So, we were looking at the Tableau method, and now we should start moving towards doing some things that are less implementation and more formal oriented. So, one of the so the first thing that I will do is in terms of for any logic, there are certain soundness and completeness requirements that you usually want to prove. Okay. And so, this so the first thing we will do for the Tableau method is to prove a consistency and completeness, and then we will get on to formal proof theory after this, and then try to prove the soundness and completeness of the proof theory, and maybe we will also look at certain other properties like compactness and so on. So, let us first establish some of the notation. So, one thing is that the first thing I would like to do is to restructure the Tableau rules. So, in general we had these Tableau rules for propositional logic, and essentially what we said was that you create a tree. A Tableau is a tree in which it is called an the Tableau actually comes from the notion of a semantic Tableau, because if you remember what it was inspired essentially by these identities which are directly related to the notion of truth or falsehood. However, this these Tableau rules go beyond the notion of a usual semantic Tableau, in the sense that they satisfy an extra property, and that is that in general the rules are such that there is a numerator and a denominator, or one or more denominators, okay. And the denominators, except for the case of this last biconditional, you can think of these denominators as essentially being sub formulae of the numerators. To the extent that sometimes of course, the notion of negation is used instead of assigning truth and falsehood, which is what happens in a semantic Tableau. So, in an analytic Tableau sometimes there are negation symbols which need to be introduced, like for example, this not psi here in this denominator is clearly not a sub formula of the numerator. However, modulo the appearance of negation symbols, they essentially satisfy what is known as the sub formula property, and that is that the denominators are usually sub formulae of the numerator. And that is what so what this gives is and the negation rule ensures that you do not have too many negations appearing, and what it also ensures therefore is that your Tableau will always guaranteed to be only a finite tree. I mean, you cannot go beyond a finite tree, and that finite tree is determined by the sum of the sizes of the formulae that were there in the root of the Tableau, that were originally there in the Tableau. So, and the Tableau rules also have two kinds of rules. When Smulyan originally defined them, he called them alpha and beta rules. I prefer to call them elongation and branching, because that is the way that helps me not to get confused. As far as I know, nobody else calls it elongation and branching. This so he called them alpha and beta rules, and basically alpha rules were of a conjunctive kind, of an and kind, and beta rules were of a disjunctive. So, essentially the elongation rules would be called alpha rules, and the branching rules would be called beta rules. And since we are dealing with binary operators, which reminds me also, these you can think of all this as single operators, right. I mean, it is not necessary to necessarily consider them as two different operators, but since we normally write them like this, we express them in terms of two different operators, but they could be considered to be a single operator. Okay. So, it has a nice structure that basically for all operators and their negations, there are rules which are either of an elongation type or of a branching type. And in a case like this, there are both rules are branching. In the case of the double negation, you might think of it either as an elongation rule or as a branching rule. It does not matter. It's trivial in either. It's trivially true in either case. Yeah. But very often it is I mean whenever it's convenient, I'll think of it as an elongation rule. At other times I might think of it as a branching rule. Okay. So essentially in that sense, so all these elongation rules are of this kind and the branching rules are of this kind, and what we can do is in order to what we can do is we can restructure the tableau. It is so essentially what we can think of a tableau as the rules as something very similar to the sets of literals sets of literals which we used for resolution. Yeah. So, one way of restructuring the tableau rules in terms of sets of formulae, which is what essentially what we are saying is, when you have an argument, that argument is converted into a set of formulae and you want to prove either the unsatisfiability of that argument or you want to prove that there is a falsifying assignment for that argument. Yeah. Okay. So, in either case we can think of the elongation rules as essentially being of these kind. So, if there is an elongation rule in the original tableau calculus of this kind, then essentially we can think of an elongation rule in which we start with a set of formulae, of which a set of formulae gamma, in which we choose one formula phi, to which to apply either an elongation rule or a branching rule, depending upon what the root operator of that formula is. Now, depending on that root operator of that formula, if it yields a psi and if it is an elongation rule, then we can just think of gamma as not having phi anymore, but instead having the two denominators psi and chi. Okay. In the case of branching, what happens is that you can think of it as creating two separate sets, remove phi, and one set of possibilities is delta union psi and the other set of possibilities delta union chi, right. And we could actually this kind of restructuring will help us in a certain way, which it makes certain proofs obvious, though it makes the tableau rules look ugly. It is actually is obvious. It also allows us to put in an extra rule which I just stated verbally, that of a closure of a closure of a path in that tableau, and that is made clear by this. So, essentially what we are saying is, usually this rule is expressed as a complementary pair of literals, but I see absolutely no reason why we cannot just take, since we are interested in the forms and the shapes of formulae, if it is obvious that there are two formulae in the original set gamma, where one formula is syntactically identical to the negation of the other, there is absolutely no reason why we cannot consider them to be complementary pairs. So, what I have done is, instead of using atoms and atoms p and not p, I am saying that you just look at the patterns of the formulae. If you find one pattern which is a negation of the other in that set of formulae, then that set of formulae is essentially inconsistent, and therefore, essentially that entire branch of that tableau can be closed with this bottom, right. Now, one of the things that so there is so now all the rules can be expressed in terms of these sets of formulae, and it allows us, there is an interesting thing which is that now I do not need to look at the entire tree that is actually generated. I need to look at only the leaves of the tree, because I am anyway carrying all the formulae. Okay. In that sense, you can think of the tree construction as an updation of the set of formulae, which from an implementation point of view is actually quite quite efficient. So, firstly we do not need to consider, we do not need to actually construct trees, okay, because you can think of this horizontal line and this vertical line as essentially boundaries which cannot be crossed, right, which was not so in the case of this in the case of the rules expressed in this form. In the case of rules expressed in this form, you always cross this horizontal line boundary, because you wanted to look for complementary pairs along the entire history of the tableau, but you were not allowed to cross this vertical line. I mean, you were not allowed to, the two parts on either side of the vertical line were not allowed to interact. There was no influence between them. Once a branching was done, essentially they went their independent way. They probably branched further, but this was like a barrier between two parts of the tableau, right. In this case, what we are saying is, by carrying all these formulas in both the numerator and the denominator, essentially we are saying that this is like just updation, okay, and I can regard this horizontal line also as a barrier. I should not go above this horizontal line ever. I have to only look at all the formulas at the leaf of the tableau. So, everything else in the tableau is just history and it is not important, right. So, that is what these rules give us. So, they allow us to actually create these barriers, and that the entire tableau is essentially a historical entity, of which what is current are only the leaves, where each leaf, each node of the tableau is decorated by, is labeled by a set of formulae, right, and each step of the tableau can be regarded as an updation of state of that, of the set of formulae. So, otherwise these rules are exactly like the original rules, yeah. Okay. Right. So, now with these new set of rules, a tableau is a tree rooted at a node containing a set gamma of formulas. Each application of an elongation rule of the form gamma down gamma prime to a leaf. Notice that now there is a gamma prime, right, because the elongation rules, instead of two formulae, became a set of formulae, set of two formulae. To a leaf gamma of the, an elongation rule to the leaf gamma of the tableau extends the path to gamma prime, right, and a branching rule actually this should be a path to include gamma prime maybe, but no, it extends the path to gamma prime, that is perfect. A branching rule of this form to a leaf gamma of the tableau extends the tableau to two leaves gamma prime and gamma double prime. Right. Okay. A path of the tableau is closed if its leaf is bottom. This is something that was not there in the original set of rules. I only stated it, but now we actually do have a rule for it, and therefore, that is basically what we are saying is you cannot extend that path anymore, because there is absolutely no rule which can be applied to this symbol. Yeah. So, right. So, the tableau is closed if every path is closed. So, essentially we should have got bottom a set of leaves, all of which are bottom, otherwise the tableau is open, which means that there is at least one open path, okay, such that to the leaf of that open path you cannot apply any rule, right. Okay. So, so a tableau which is I have not, but maybe it will come later. So, we will say a completed tableau is a tableau in which no rule is applicable on any of the leaves. So, a completed tableau could have either closed paths or even or some open paths, right. Okay. So, now, so as I said, the problem of validity of
So, what is the consequence of a tableau being complete but having open parts?
Yeah, we will come to that. It has to do with satisfiability. Right? Okay. So, as a set gamma of formulas, since the notion of validity of arguments and logical consequence and so on has been reduced to that of satisfiability of a set of formulae, we will say a set of formulas is consistent if it is satisfiable. That means, there is a truth assignment under which every formula of the set is true for the same truth assignment. So, one thing is, each tableau rule preserves satisfiability in the following sense. Now that we are dealing with sets of formulas, we have to look at the notion of satisfiability in a more precise fashion for a set of formulas. In the case of elongation rules, if the numerator gamma is satisfiable, then so is the denominator gamma prime. In the case of branching rules, if the numerator gamma is satisfiable, then at least one of the denominators is also satisfiable. Okay. So, there is the construction of the tableau in effect gives you something which is disjunctive in nature. So, you are talking about essentially an OR of ANDs of formulae without actually going into negation, without actually going into normal forms. So, it is actually a disjunction of conjunctions, and so it is satisfiable if at least one of the denominators is satisfiable. Okay. Now, so one thing is, so you can the proof is very simple. You just take an arbitrary truth assignment which for which gamma is true, and show that therefore, if a chosen phi, a formula phi in that gamma is true, and an elongation rule has been applied, then by case analysis you know the denominators, and you can show that each of them would also be true if that original phi was true, right. Similarly, in the case of branching rules, again you can do a case analysis on the operators which are actually branching, which actually give you branching rules, and show that if one of them is true, then if the original formula phi is true, then the two derived formulae of the two derived formulae psi and chi, at least one of them would be true, right. Okay. So, we will not go into it too much. So, we would say a tableau is completed if no leaf in any path may be extended, which means that there is absolutely no rule that is applicable on any of the leaves. Yeah. And if gamma is satisfiable, then there exists a completed tableau rooted at gamma, which has a satisfiable leaf. So, so that should answer your question. A completed tableau in which you have not derived, in which there is at least one path which does not have bottom in it as a leaf, is a satisfiable leaf. Yeah, and if there is no rule applicable, right. And a set gamma is unsatisfiable if there exists a closed tableau rooted at gamma, which means every path ends in a bottom, then the tableau is unsatisfied. Then the original set of formulae gamma that you started with is unsatisfiable. So, the main question in this particular case is, for a given set gamma, there could be many different tableau, because it all depends on what formula phi in the set of formulas I choose as a candidate on which to apply a rule. So, that is a very highly non-deterministic choice which can allow for multiple tableaus, right. And what we have said here is that essentially if I can find one closed tableau, then we will say that the set gamma is unsatisfiable. That is what this says, but then there is the question of, is it true that there exists other tableaus for the same set gamma which have open completed tableaus which have open paths. When that is some, so the issue of completeness is really this question in the case of tableau. Consider all the tableaus that I have, and the second issue and the more important issue of completeness actually is the question of, take any tautology of propositional logic, can I prove that it is a tautology using the tableau method, right. The issue of completeness there is, can I prove for every tautology that there is a tableau which will establish that it is a tautology. In order to establish that a formula is a tautology, it is necessary for me to be able to take the negation of the formula and use the tableau method to prove that it is unsatisfiable. Okay. If I can prove, supposing for every tautology there does exist a tableau which proves it, which means which proves that its negation is unsatisfiable, is it guaranteed that every tableau for that formula is also guaranteed to be unsatisfiable? If we can prove this, then essentially then the question of completeness for logical arguments is automatically answered. If every tautology can be proven using the tableau method, then every valid argument, the validity of every valid argument can be established, right. So essentially so these are the questions for which we require some basic machinery to be established at propositional logic level itself. So that it becomes easier for us to handle these questions at when we come up with more complicated logics. Yeah. So it will seem obvious to you at the propositional logic level, but we will bring in some machinery which we will use later also for other logics. Right. So the main question now is so the main questions are essentially, can I establish the tautologousness of every tautology? For a given tautology, is there a tableau which does not establish its tautologousness, and if so, then what do I do with it? And the second important question which is hidden, but is as important as we did for the case of tautology checking is, supposing I have got a formula which is not a tautology, then can I prove that it is not a tautology by getting a completed tableau and a truth assignment for its negation. Supposing I have a formula phi which I want to prove to be a tautology, which means I attempt a tableau using the formula not phi. Okay. Now, if phi is not a tautology, then not phi is not a contradiction. Okay. If not phi is not a contradiction, then it has a satisfying truth assignment, and therefore, is it possible to find a satisfying truth assignment. This is the equivalent of establishing a counter example when you claim that something does not hold. Yeah. So, hidden in all these notions of completeness and are these two facts, not just whether I can prove all tautologies are complete, but also for all formulae which are not tautologies, can I establish a satisfying truth assignment. So, these are important questions, and then the next question is, given that a tautology, even if every tautology is provable by Tableau, are there tableaus for those tautologies which are completed, but which are not closed? So, this corollary 9.5 just says that a set is unsatisfiable if there exists a closed tableau rooted at gamma. Are there other tableaus rooted at gamma which are not closed? I mean, that is, yeah. So, these are the kinds of questions for which we have to establish machinery to answer these questions. Yeah. So, the issues of completeness and so on are not just are not totally obvious. There are deeper things. One is that of finding counterexamples. Another is that of checking whether, I mean, is this corollary only says it is like looking for a needle in an infinite haystack. Yeah. I mean, how do I know that there are not other tableaus which are completed tableaus which are not closed? Yeah, and I have to establish those things, right. Okay. So, the machinery we will start with is something known as Hintikka sets. Yeah. So, a finite or infinite set, by the way, now it does not when we are looking at this, when we are looking at tableaus, of course, we are looking at finite sets, okay. But in general you can have an infinite set of formulae. For example, there is enough mathematics out there where certain theorems do not have finite proofs, okay, where you require what are known as infinitary proof rules in order to establish a proof for those theorems, right. So, there are such things that happen in mathematics, and so therefore, it is perfectly reasonable to also consider infinite sets of formulae. Yeah. So, a finite or infinite set gamma is a Hintikka set named after the logician Hintikka who studied these things. So, one is that it should not have bottom in it and it should not have any complementary pair. Okay. So, here I have gone back to complementary pair of literals, but essentially it means that let us go back to this. Let us go back to this. The point is, if phi is not an atom, it is some complicated formula, and you have both phi and not phi in this set, then what actually would happen is, even if I replace this rule by having only atoms p and not p here, then phi and not phi by application of all these rules actually eventually will yield a complementary pair of literals. So, this rule is just like a shortcut, short circuiting that process. If you can see right from the start that one complicated formula is obviously a negation of another complicated formula, you might as well stop the process right there. It is a short circuiting process rather than being rigorous. All formulations of Tableau rules will actually have complementary pairs of literals here rather than general formulae. Yeah. Okay. So, right. So, so it should so this set gamma should not have a complementary pair, and if phi is essentially a multiplicative kind of formula, okay, the there is a way of looking at, you look at those operators, basically 10 operators, we can think of them as either additive or multiplicative. In fact, the ones which have elongation rules are multiplicative operators, and the ones which have branching rules are additive operators. Yeah. So, So, I am looking at these as operators, not of or, not of arrow. Okay. So, we are essentially saying that the formula will be of the form not of psi arrow chi, but I am looking at this as a single operator not of arrow. Yeah. Similarly, in the case of not of or, similarly in the case of not of and so on. So, this these if phi is a multiplicator is actually the root, if you look at phi as an abstract syntax tree and its root operator is multiplicative, that means it is one of these. So, which means that you have to go one step down through negation also in order to determine whether it is multiplicative or additive. Okay. Then there is a psi prime chi prime which also belongs to gamma. If it is a multiplicative operator, then there are two formulae of the form psi o dot chi, then there is a psi prime chi prime also belonging to gamma, and if it is an additive operator psi chi, where the additive operators are these, right, then one of this intersection says that one of psi prime or chi prime should be in gamma, right. Yeah, this what we are saying is that it cannot be the case that neither psi prime nor chi prime is in gamma. Yeah. So, the psi prime and chi prime in each case for the multiplicative operators and the additive operators are defined actually here, right. And if you look at this table exactly corresponds to the Tableau rules. For the multiplicative operators correspond exactly to the elongation rules and the additive operators correspond exactly to the branching rules, and the two components in the denominator are the psi prime and chi prime, right. Okay. So, this is how we will define a Hintikka set. So, essentially a Hintikka set is a set which is what is known as downward saturated. Yeah. So, they are downward saturated in the sense downward is because you are looking at essentially sub formulae, and what the motivation for constructing Hintikka sets is actually to look at some maximal set of sub formulae which are satisfiable. Yeah. So, if a set gamma is satisfiable, what I can do, okay, let me start with some set delta. If all the formulas in that set delta are satisfiable, then what I can do is I can saturate that set by closing it under these conditions. These are the Hintikka conditions. So, firstly, if it is satisfiable, then it cannot have bottom in it, okay, and it cannot have a complementary pair in it, right. And therefore, and actually it cannot even have any pair of formulae which are complements of each other. But more importantly, what I saturate it essentially on formulas of smaller size, which preserve certain satisfiability properties. So, essentially if the original So, I can actually define for any set delta so for any set delta I can define the Hintikka operator h of delta such that essentially these three conditions hold, right. So, it includes, so this is some set gamma such that if delta has a formula of the form phi is some psi some operator chi, then depending on whether this operator is additive or multiplicative, the corresponding psi prime and chi prime are also added into the set. So, I can think of a Hintikka operator H which closes any set of formulae on such that these conditions hold, right. So, that is an alternative definition of a Hintikka set. So, I can convert. So, essentially this set H of delta, even if delta is not originally a Hintikka set, this set H of delta will become a Hintikka set. And it is clear that the Hintikka set this operator H is a closure operation, because you apply this operator twice, you do not get anything new, you only get H of delta. So, it is a closure operation and closure operations are are also called saturation operations, and not only is it a closure, it is a downward closure. So, in that sense you are saturating the set downward by taking essentially formulas of smaller degree than the original formula. So, you are populating the set with a formula of smaller degree, right. So, it is downward saturated in that sense, right. So, we will so this is the way the saturation proceeds. If there is a formula of the form psi and chi, then include both psi and chi in the formula, that is from step 2. If a formula is of the form psi or chi, then choose one of them and put that in the set. So, actually this Hintikka operator will give me a set of sets of formulae, because for all the additive operations there are two possible sets which can be obtained. Yeah. So, but each of them will be a Hintikka set. Okay. So, this actually so this formulation is not exactly correct. It has to be that this H gives me a set of sets of formulae, where each element of that set of sets of formulae is a Hintikka set by itself, and therefore satisfies this downward closure property, downward saturation property. Yeah. Okay. Right. So, then you have Hintikka's lemma, which essentially has to do with satisfiability. So, let gamma be a Hintikka set. So, that means it satisfies those three properties. For any atom P, since the complementary pairs are not included in that gamma, if it is a Hintikka set, there cannot be any complementary pairs. We take a truth assignment, where such that if P is positive, then we assign it 1, and if it is P occurs negatively, then we assign it 0. For all other atoms, we just choose any value, any truth value, we choose either 1 or 0 randomly, it does not matter. Okay. So, then you can show by induction on the degree of a formula, and this is a formal definition of a degree. Basically, I am not it's like size, except that I am not including negation. Yeah. So, the degree of each atom is 0, the degree of negation of formula is just the degree of the formula itself, and for any other binary operator the degree increases by 1. You take the sum of the degrees of the components and increase it by 1. So, it is not exactly the size of the formula, because for negation I have, because I have firstly for atoms I am saying the degree is 0, and for negation I am not increasing the degree. So, it is not the size of the formula, but the notion of size can be defined similarly, right. Okay. So what you can show by induction on the degree of the formulae in gamma is that each formula in gamma is satisfiable if on this truth assignment, right. I am not going to formally prove it by induction, because this is it's sort of clear. Yeah. Okay. So, essentially Hintikka sets are satisfiable sets, right, and so let us take here I am going to consider the new formulation of the tableau rules, right, as sets of formulae. So, take a completed tableau and take an open path. So, supposing there is an open path in the completed tableau, take the open path and look at all the formulae in that open path. The union of all those formulae is a Hintikka set, right, and that is because the table for the construction of downward saturated sets exactly is mimicked by the tableau rules, right, for inclusion. The only problem was in each of these applications the original rule was removed from the set of rules. That is why I am taking a union over the entire path, yeah, to restore back the original formulae which got split by the sub formula property, right. So, if I take all the original formulae and so basically so there is another way of looking at it. If I look at all these rules, there is a third formulation which we can do. If I look at all these rules as of this kind, delta union let us say phi and psi, let us take this, okay, and I actually write it as delta union phi and psi and include phi and include psi for a typical elongation rule. Then what I will be, then I do not need to consider the entire path. Okay. Similarly, for this is in the case of elongation rules. In the case of a branching rule like this, if I had phi or psi, if I think of this as delta union phi or psi and I include phi, delta union phi or psi and I include psi, I could do this, in which case I would have reformulated the theorem as saying essentially every leaf in the tableau. If this is how my tableau rules go, then the theorem would be restated as essentially I do not need to consider the entire path, I just need to consider a leaf, and that is like, and this is like a downward closure operation. Yeah. Right. So, since I am considering the tableau rules too, I have to take the union over an entire path, and that is a Hintikka set. Yeah. So, you can prove that each rule in the tableau rules too creates a path for the construction of Hintikka sets, right. Okay. So, that is the relationship between tableaus and Hintikka sets, and now we have the completeness. So, first thing, If phi is a tautology, then every completed tableau rooted at not phi is closed. Okay. That is very simple. Let T be a completed tableau rooted at not phi, which is open. So, we are proving it by contradiction. If it is open, then by this corollary 9.4, this must be satisfied, it has a satisfiable leaf, right. Okay. So, which means that phi cannot be a tautology, okay. And therefore, therefore, it means that if phi is a tautology, then this tableau must be closed, right. Secondly, every tautology is provable by the tableau method, and that is that if phi is a tautology that cannot be proved by the tableau method, there must exist a completed tableau rooted at not phi which has an open path, but if it has an open path, then that implies that not phi is satisfiable, and this which will in turn imply that phi is not a tautology, right. Okay. So, this completeness, so essentially what it, therefore, what this shows is that it gives us, it answers this original question that we raised, that you take any unsatisfiable set, you take any tableau rooted at that unsatisfiable set, it does not matter, you will, the tableau will eventually close, every path will get closed, right. So, this is, and this is essentially saying that there is a certain sense in which proofs by contradiction are actually easier to perform, because they are somewhat more deterministic. They are actually goal directed by taking by so in general, when you take any mathematical proof, there is a possibility of going directly, right. One is you take the hypothesis and start trying to derive the conclusion, but the problem with that could be that you might actually go off onto some tangents and never lead, which will never lead to the conclusion. I mean, you may prove a lot of other interesting lemmas and theorems in the process, but you may not have ever proved the original theorem. Whereas, if you try to prove by contradiction, there is a good chance that your proof is goal directed, because what you are going to do is you are going to take the hypothesis and the negation of the conclusion and try to prove a contradiction. So, it is much more goal directed, right. So, that is the reason why these methods like resolution and tableau actually work so well, and that is because of this theorem, which essentially tells you that every tableau for an unsatisfiable formula will close. Right, and therefore, the tableau method is complete. So, by essentially by Hintikka sets, what you are saying is that if the tableau is open, then you take any open path in that tableau, that is a Hintikka set, and what the previous lemma tells you is I can find a satisfying assignment for that Hintikka set. If I can find a satisfying assignment for that Hintikka set, then I can definitely find a satisfying assignment for the original set of formulae, right. And that satisfying assignment is very easily determined from the Hintikka set by just looking at all the atoms, all the literals that occur in the Hintikka set. Throw away all the complicated formulae. Finally, in order to find a satisfying truth assignment, just look at the literals in the Hintikka set, and that is the satisfying assignment, that is defined by this. So, your tableau method is complete, and in a similar fashion actually the resolution method is also complete. Okay. The tableau method is complete in the sense that for every tautology So, firstly every logical argument can be converted into a set of formulae such that the argument is valid if and only if this set of formulae is unsatisfiable. Secondly, for every set of unsatisfiable formulae, every tableau will close, and for every set of consistent formulae, every open path in every tableau will actually give you a truth assignment which satisfies the original set, right. That is, so that is what this completeness does. And many proofs of completeness in modal logics and first order logic will actually use the notion of Hintikka sets and downward saturation. The important thing about that downward saturation is that finally you have to look at only the literals, and in order to find a satisfying assignment, you just require this, right. Yeah. So, are there any questions? So, the first assignment I have not been able to put it up because somehow the network was not working. You have to implement Tableau method for propositional logic. As soon as I can, I will put up the formal data type. The data type is the same as that in the tautology checker. I have not had the time to correct that link that you mentioned, but I will correct it today. Yeah. So that you can, the tautology checker source code is at least available to you. So, you use the same data type and use the same signature that we use for the tautology checker, you also use it to implement tableaus. And you have a choice, you can implement the tableau either by the first set of rules or by the second set of rules or even by this third set of rules, it does not matter to me. But this third set of rules will be carrying baggage, which is in the second set of rules, at least it's just like state updation, and that might be there, or you can, if you have the you can also use the first set of rules, but implement one Tableau rule and in as efficient as possible, so that we have a Tableau method for propositional logic. Yeah. And submission formalities and so on and so forth will come through the Moodle and the department. Okay. I think the institute Moodle is not working. So, the Moodle in the department running on JJ1T, which means that you have to be in the institute when you submit, because the JJ1T will not be visible outside the institute. Yeah. So, you have to be in the institute when you submit, right. So, that is that I hope will set that right. Yeah. Okay. So, then we will do compactness next time, and then we will start first order logic and proof theory, or we will start with proof theory and then first order logic.